Welcome everyone. Welcome back for the third and last installation of this webinar series. It's called The Frontiers and the Challenges. We'll see what is possible with density functional theory and actually what are some of the limitations, either in terms of accuracy or in terms of the fact that some of the properties that we're interested in go beyond what the density functional can give us. Now, from the first webinar on Wednesday, I think you have understood that what we are doing is actually a theory of the ground state energy. So in principle, if we had the exact exchange correlation functional, we would be able to get the exact ground state energy. We don't know what the exact exchange correlation functional is, and so I'll discuss briefly in a moment what are some of the approximation, and in particular how those approximations propagate towards the properties that might be complex properties that we calculate. So whenever we want to do some material simulations, typically we need to understand what is the origin of the property that we want to calculate. It is electronic, is it atomistic, where does it come from? And often we need to make sure that we are actually taking into account what would be the realistic conditions of the material or the device we are studying. And I'll show you examples on how we can start thinking of introducing the effects of temperature, pressure, composition, the thermodynamic ensembles, study liquids, and so on and so forth. So in general, some of the core examples have to do with extending density functional theory simulation from just calculating the total energy of a material to calculating the thermodynamical property of that material. So that could be, studying the material at a given temperature under a certain pressure. We have already seen example of the equation of state and looking at two states that have the same enthalpy, studying the effect of the chemical potential, or for a gas, the partial pressure, electrochemical potential, pH, and so on and so forth. One of the important messages that I've given you is that when we do a Kohn-Sham density functional theory calculation, actually the Kohn-Sham electrons are there just to give us an approximation to the quantum kinetic energy. So they are not the real electrons. For a number of reasons, they are not completely different from what the real electrons are. But if we want to calculate spectral properties, that is, if we want to calculate, say, what is the photoemission energy that we have when we take an electron out from the interacting system, that would mean what is the band structure of a material, we cannot really do a density functional theory calculations that can give us an idea, but it's just not the real thing. And the real thing can be obtained in different ways. The sort of mainstream approach is that of many-body perturbation theory. With perturbation theory and resumming infinite series in a very smart way, we transform these Kohn-Sham electrons into real electrons. And so from there we can actually calculate spectral properties. This is often called the GW approach from the main terms that are kept in the perturbation expansion. And these days there are many codes and even open source codes like Yambo that allow you to do these calculations or Berkeley GW fairly easily, at least for small systems. There are other approaches. I've mentioned the quantum chemistry approaches. I've mentioned the quantum Monte Carlo approaches that could be used to get you excited states. And there are also spectral approaches that try to take into account correlation of electrons, like dynamical mean field theory and these higher order or cluster expansions that try to go beyond, say, what the exchange correlation potential of DFT does on one side, that is treat better a correlated system, but also give you spectral properties. Then other classes of properties that are very important in material science have to do with events that take place onto length scale that are too large for direct simulation, or on time scales that are too long. An example of the first could come from, say, the strength of metals. In a real metal, what we have is really a polycrystalline assembly with grain boundaries sliding, with dislocations locking up, and this cannot be addressed directly with ab initio simulations. A lot of progress has been made by computational material science in the last 20-30 years in understanding what are the most important microscopic phenomena that we can use to actually understand property like the strength of a metal. I think as we go forward, one of the most interesting approaches will be one in which we actually use ideas from machine learning, like a neural network, a Gaussian approximation potential, to take hundreds, thousands, most likely hundreds of thousands of ab initio calculation, and on that fit a neural network or represent a kernel, and then use the kernel regression method, use the neural network to actually do maybe brute force simulation on system that starts to have the length scales of tens, hundreds of thousands of atoms that we need to study some of those more complex phenomena. The problem of timescale is also easy to explain. I think at polypeptide chain folding into the natural state of a protein. This is a process that might take a few seconds in real life. But of course, if we pretend to study that from anatomistic simulation, following what each and every atom is doing, apart from the just size of the protein, it's going to take, since that every vibration at the atomic level takes place on the scale of the tens of femtoseconds, so we need, to accelerate from, femtoseconds to seconds, and that's 15 order of magnitude. So that's very challenging. Examples, others that are also complex and that I'll mention later, have to do with the sampling of phases and compositions. Say it could be an organic solar cells where you need to find out what is a typical equilibrium or maybe kinetically trapped configuration of your polymer, or it might be a composition temperature phase diagram of an alloy where you need to understand how energy and entropy balance each other to determine the stability of a certain phase. And so for all of this, we need really to use our intelligence, and we need to develop methods that allow us to bridge scales like multi-scale methods, to be aggressive in addressing larger length scales, like developing methods for density function theory that scale as the size of the system linearly instead of cubic, so being able to address with direct DFT calculations thousands of atoms, systems that accelerate our time scale sampling, like metadynamics, or methods that allows us to explore different phases and compositions, like minima hopping and random structure searches. And that's the last example of interesting things that we can do, and that's one of my favorite, is really calculate complex properties of materials. You'll see examples. There's I've already mentioned phase diagram as an example of composition sampling. I'm particularly fond of spectroscopies because predicting spectroscopic data allows for a very sharp comparison between theory and experiments. Think at a Raman peak that is usually measured in experiments with very high accuracy. Well, either we get it in simulation or we don't get it, and if we do not get it, it could be for different reasons. Maybe because our microscopic representation of the material is not correct, and maybe the physics is not correct. And I mentioned here vibrational spectroscopies like infrared or Raman, X-ray spectroscopies like extended absorption near field emission spectroscopy, magnetic spectroscopies like nuclear magnetic resonance or electron paramagnetic resonance, photoemission spectroscopies or microscopies. You know, we might want to represent the image that could be seen in a transmission electron microscope, or that we could observe in a scanning tunneling experiment. Examples that I will also show later on have to do with transport, that is a typical multi-scale and even multi-physics properties in which we want to understand how an electrical current or heat is conducted by a solid. So this is just a very broad overview. Let me go back for a moment to the issue just of the accuracy in the total energies that we can calculate. You already know that if we add the exact exchange correlation functional, we would get the exact total energy for anything. We would get the exact total energy for a strongly correlated material, for a high TC superconductor, for anything. We don't have that, and as I said, you know, building new ideas in exchange correlation functional requires a lot of understanding, a lot of insight, and in general imposing well-known properties that might be coming from molecules, might be coming from the homogeneous electron gas, has been very important in developing some of the most used exchange correlation functionals in the solid state. So I've already, you know, mentioned yesterday how we went from the local density approximation to the generalized gradient approximation to the Laplacians, what are called meta-GGAs, and then there are more complex approaches. I'll discuss hybrid functionals with a fraction of Hartree-Fock exchange later on today. So I'll just stop here up to the meta-GGA, and I'll present this comparison of a few properties between one of the most commonly used functionals in the solid state, PBE, a generalized gradient approximation from 1996, and a meta-GGA scan, the strongly constrained and property normalized functional that was introduced, both of them actually by John Perdue and collaborator. Scan is from 2015. This is a nice study from Chris Wolverton that goes over 1,000 materials out of his OQMD database, and these are materials for which accurate experimental data are present and that span many different classes, insulators, metals, magnetic materials, and so on and so forth. And here maybe we want to focus on the yellow column. These are the mean absolute relative errors. So we have 5% maybe for PBE and a little bit above 3% for scan of absolute relative error in the equilibrium volume. So getting a 3% error in the equilibrium volume means that we are getting a 1% average accuracy in the lattice parameter. So I would say we are doing very well. And you see that, you know, PB is already good and scan is even better. Let me show you another property. In this case, something that is actually much more difficult. These are formation energies of compounds. So to calculate precisely a formation energy, you need to understand what is the energy, and that's you know, done in the experiments with thermodynamic measurements, with thermocalorimetry, but you need to understand what is the difference between the energy of a compound with respect to the energy of its constituents in the normal states. So if it was, you know, lead titanate, a perovskite, you need to know what is the energy of the metal lead, the metal titanium, the oxygen gas, and the compound. You need to be careful about entropy in the gas, and so on and so forth. And this is the comparison and the relative errors with respect to experiments for a couple of accurate experimental databases. The IIT and the SSUB are two databases. And you see, in general, blue, that is PB, does a good job. Scan does I would say, a significantly better job. You see, it's really peaked around 0 error. It's very even. But of course, predicting these properties accurately is actually quite a challenge, and you see there are errors, and sometimes those errors could also be in the experimental database. It's not easy to measure this formation energies very accurately, but you see that scan has a number of outliers, PB is another number of outliers, and in general, we are talking about errors that can easily reach 50% with respect to the experimental value. And the last example has to do with the band gap in the cone-sham band structure with respect to the true experimental band gap. This would be again the band gap that we would measure in a photoemission experiment or in a transport experiment. So it's not the optical band gap that could have other like excitonic effects in it. So we are comparing cone-sham fictitious electrons with the real world. So there is no reason, and actually I'll mention it later, it shouldn't agree. But this is just to say, if you try to look at a band structure from, say, PB or scan, is it a good proxy for the band structure that you would measure in an experiment? Well, look at this. These are all systems that have a 0 calculated band gap, so they are metals, and they have a 5 electron volt band gap in the experiments. So there can be very large discrepancies that are qualitative. They shouldn't really worry us. We are trying to reproduce the energy of the material, but this is just a caveat if you're trying to do band gap calculations. So I didn't want to go deeper into the zoology of functionals. I should just mention that one of the important developments that has happened in the last 10-15 years, driven originally especially by David Landgraf in Rutgers and Ben Lundquist in Chalmers, has been the development of functionals that are also able to take into account van der Waals interactions. Van der Waals interactions are very difficult to reproduce just from a function of the density. Think at two, say, maybe noble gas atoms. As they, I move them far apart, they're going to interact with an interaction that decays as, the inverse of the 6th power of the distance. But actually, the charge densities of these two atoms are going to decay exponentially. So very quickly, there is no charge density in the middle, and there is no way for the charge density to know how one atom is distant from the other. So that was a challenge, but by now it's a success story. I apologize, I don't have slides here, but right now there is a variety of functionals that are also able to quite carefully describe van der Waals bound solids. So one typical example would be graphite, where the distance between the layers is driven by van der Waals interactions. And if you were to do, say, a PB calculation, that would be greatly overestimated. LDA historically got the right distance just out of luck, because LDA tends to slightly overbind the solids, and that was just enough to get, let's say, the right result for the wrong reason. But rather than going into the accuracy of these fundamental quantities, what I want to discuss today is actually the more complex properties that we can calculate with these tools and how accurate we can be in those. It's much more difficult to be systematic there, because these calculations tends to be expensive and complex. So it's not like doing 1,000 band gaps, but more and more, I think, in the future we'll have an automated way to also calculate these complex properties, and so start to get some statistics. But as a first thing, let me sort of go back actually to fundamental quantum mechanics and make a first step to look at something that goes beyond the energy of a material. And this is a very beautiful piece of work. Of course, the guy was Richard Feynman. At the time, he was probably 22 or something. He was doing his bachelor in physics at MIT. The year was 1939, and you might recognize the signature here of John Slater, of the Slater determinant, that was the instructor in charge of the thesis. And Richard Feynman comes out with this beautiful theorem that we will use a lot, that is true in general in quantum mechanics. And at the same time, also Hellmann, actually 2 years earlier, had published it. So it goes under the name of the Hellmann-Feynman theorem. And it's written here. I'll demonstrate it in a moment. It's very simple. It has to do with the derivative of the energy. And say the force would be minus the derivative of the energy with respect to an atomic displacement. So that's why it's called forces and stresses in a molecule. Let me actually show you more formally in a bracket notation what is the Hellmann-Feynman theorem. It concerns itself with the derivative of an expectation value, the total energy, with respect to any parameter that enters a Hamiltonian. We have consider for a moment lambda being the force, but it could be anything else. And what Feynman and Hellmann proved is that if you want to calculate this derivative, you just need to take the expectation value of the derivative of the operator. And say if I was concerned about the force, and that's what I had written before, the Hamiltonian here would just be the kinetic energy plus the potential energy, say in a molecule. The kinetic energy does not depend on the position of the atoms, and so the only thing that enters is the derivative of the potential energy, and that's what we calculate. So you see, if we have the ground state charge density n, it's very simple to calculate derivative of the energy. We just take the expectation value of the charge density times the derivative of the Hamiltonian with respect to the parameter. And proving this is actually very simple and fun, so I'll just do it for you here. So what we are doing here, think at first quantization, we are deriving an integral of psi star h psi. So what we really have are three terms. The derivative of the first term plus the derivative of the second term plus the derivative of the third term. But now look at what I have here. I am at the ground state. So h psi is equal to e psi, and same here for the ket. So the first and the third term can be condensed into saying I have E that multiplies the derivative of psi with respect to lambda times psi plus psi, the derivative of psi with respect to lambda, plus the expectation value of psi in dh, the lambda psi. And the beauty here is that this term in the parentheses is actually equal to the derivative with respect to lambda of psi psi. Because you see, if I expand this derivative with respect to lambda of psi psi, I get exactly what I have in the parentheses. But psi psi is normalized, is equal to 1, so this derivative is equal to 0. So this term is 0, and I'm left with the proof. So it's very easy to calculate forces in quantum mechanics, and we can use that, say, to calculate what is the equilibrium geometry of a molecule, or what is the equilibrium geometry of the atoms in a very complex structure, because we calculated the self-consistent ground state energy, the Slater determinant, the charge density, and then it's very easy to calculate this integral. And this could be done, say, for the force, but lambda could also be, say, the second order stress strain tensor, and so that would give us the stress, and so calculating the stress allows us not only to move atoms to find their microscopic equilibrium position, but to change the geometry of our primitive unit cell to find out what is its equilibrium geometry, its equilibrium volume, its equilibrium lattice parameter. And we can actually go one step further, that is, we can use Hellmann-Feynman theorem to actually look, and this is what is called linear response theory, at the higher order expansion of the energy with respect to a perturbation. So I've written here a bit more formally, that is, suppose that I take my potential and I change it with a perturbation delta V with a strength lambda. Again, this could be a displacement of an atom. Delta V would give me the direction under which I displace the atom, and lambda gives me the amount of displacement. So we are perturbing our potential V0 with a perturbation that we write as a linear term, lambda, how much of the perturbation delta V. So what happens is that in response to the perturbation, say for a finite small lambda, the ground state charge density is going to change. It's not going to be n0 anymore, but it's going to be something else, n lambda, that now, if lambda is small, I can expand as a Taylor series in this perturbation, and this first order term, that is the first order change, this is in the limit of lambda 0 would be the dominant term, we call it the linear response term. So that's why this is called linear response theory. And now we can use Hellmann-Feynman theorem, and we can show that if we were to do, a expansion of the total energy in higher orders, and we substitute what I've just written, in order to get the energy correct up to the second order in the perturbation, lambda square, the only thing that one needs to know is the linear response in the charge density. So you see, the ground state charge density with respect to the perturbation gives you the first order response, and the linear response with respect to the perturbation gives you the second order response. And actually there is something called the 2n+1 theorem that was developed by Gons and Vigneron that says that actually with a more complex expression that we are not going in here, the linear response gives us the total energy up to the third order, so that can be used also to calculate the third order derivatives. But we'll focus here on second order derivatives. Those are important because, as you'll see in a moment, we can use them to calculate vibrational frequencies. Exactly as in, say, a molecule, if the potential energy surface of a molecule is this, and I am at equilibrium, around equilibrium, the energy can be expanded as a quadratic form that is 1/2 k, let's say delta x square, where delta x is the displacement from the equilibrium position, and then the harmonic frequency is given by the square root of the displacement hook law, the k elastic restoring force, divided by the reduced mass of the molecule. So understanding what is the second derivative of the energy, this dashed curve with respect to equilibrium, is something that gives us vibrational frequencies. Now, before I show you, say, the accuracy of density functional theory in doing that, let me just very briefly tell you how we get actually this linear response term. I told you how we can solve the Kohn-Sham equations to get the ground state charge density. How do we get the linear response. Well, that was done by Stefano Baroni more than 30 years ago. It's called linear response theory. And basically, it amounts to linearizing the Kohn-Sham equation with respect to the perturbation. So you see, if we have this perturbation delta V, that perturbation introduces a change not only in the external potential, that's what the perturbation here, but also in the self-consistent Kohn-Sham potential that is given by the sum of the external, the Hartree, and the exchange correlation potential. And up to linear order, this delta V in the self-consistent potential can be written in terms of the delta N, the linear response in the charge density. And in itself, the linear response in the charge density comes out from linearizing those Kohn-Sham equation, where the linear response in the wave function basically can be obtained by looking at what has been their contribution to the change in the Hamiltonian. And from this linear response in the wave function, you get back the linear response in the charge density. And if I go back for a moment with that linear response in the charge density, I can get the energy up to the second order. And with the energy up to the second order, I can get vibrational frequencies. And the vibrational frequencies in a solid are a bit more complex than a molecule, exactly like electrons in a solids don't just have atomic or molecular states with integer indices, but they have bands with, again, integer indices, but also a block quasi-momentum that is a continuum vector in the first Brillouin zone, and really tells me what is the change in phasing going from one unit cell to the other. For vibration, we have the same representation. Here we have a diamond. So diamond is an FCC lattice with 2 carbon atoms per unit cell. So we are in 3 dimensions. So if we had just a carbon dimer in 3 dimensions, so a free molecule, it would have 6 degrees of freedom. And then, of course, certain degrees of freedom, there would be 3 degrees of freedom that are translational and 2 degrees of freedoms that are rotationals, that don't change the energy of the dimer. So you would actually have only 1 independent degree of freedom in the dimer, that is the interatomic distance. But for the solid, there are, in this case, no let's say degrees of freedom that go to 0, unless I'll mention it a moment in the long wavelength acoustic limit. So in general, these 6 degrees of freedom give rise to 6 vibrational bands, or 6 vibrational branches, 1, 2, 3, 4, 5, 6. And as a function of the block quasi-momentum, that is as a function of the phasing going from one unit cell to the other, we have the entire set of dispersion. With the caveat that if we go in the longer wavelength limit, where there is no phase change in going from one unit cell to the other, then 3 of the degrees of freedom corresponds to translation, and they go to 0, and the others corresponds to the so-called optical stretching of the molecule that has a frequency around 1300 centimeters to the -1. I think for those of you that are into these things, the conversion factor is that 1 electron volt of energy corresponds to 8,000 something centimeters to the -1. So, and if we know that room temperature is roughly, let's say, 1/40th of an electron volt, room temperature is roughly equivalent to 200 centimeters to the -1. That means that in a piece of diamond at room temperature, if you look at that engagement ring, what you get is that only actually these vibrational states are excited, and all these other vibrational states are dead. Not to mention that if you wait long enough, your diamond will become graphite, because that's the thermodynamically stable state at ambient pressure. Anyhow, the message here was that actually, these vibrational frequencies of the phonon dispersions can be calculated with great accuracy. This is in black, just a GGA calculation using linear response theory, what we often call density functional perturbation theory. And the agreement with the experimental data is actually very, very good. In red are the experimental data. Those were obtained with a source of neutrons at the time. These are from the 60s. You really need a nuclear reactor. These days you can have other spallation sources. But the black dots can basically be done on your desk. Sorry, the black lines can be done on your desktop computer. So much, much simpler. And without really going into the theory, but one can also calculate more complex vibrational spectroscopies. Not only one could calculate, say, the vibrational frequency or the intensity of a Raman peak, that is what is measured, say, in Raman spectroscopy, but one can even measure what is the change as a function of temperature of a Raman peak, where here we have a couple of examples. Maybe graphite has more experimental data, and what we have here in a solid red is the theoretical prediction, and the little crosses are the experimental data. And the vibrational frequency changes because the material expands or contracts with temperature. Graphene actually strongly contracts with temperature. That means that is a optical frequency, because you're shrinking it, actually go up. That is what we call a blue shift. But then you have to do the theory of the interaction of vibrations with light, and you discover that at finite temperature, those peaks are influenced in equal measure by processes that involve 3 phonons and 4 phonons in the language of second quantization. So you need to calculate third order derivatives with the 2n+1 theorem. Fourth order derivatives for the 4 phonon processes are a bit too complicated to calculate with perturbative approaches, but you can do it with finite differences of the third order derivatives. And when you put everything together, and the 3 phonons and 4 phonons term enter with the same order in the expansion, that's why they are both relevant. It's not that the 5 phonons, the 5th order term would be equally relevant. When you do that, you start to have a very, very good agreement with experiments. Another example of spectroscopies that I like is the one of magnetic spectroscopies. You're probably familiar with the idea of nuclear magnetic resonance, but basically what happens is that, say, in a molecule, or in this case, in a solid, what happens when you apply a magnetic field is that that magnetic field will induce some current that screen the applied magnetic field, and those currents are very local. So every atom will experience a different counter screening electronic current, and we can actually measure for certain nuclei what is the magnetic field that those nuclei feel by measuring the transition of those nuclei that have themselves a magnetic dipole. And I mean, this has been a Nobel Prize matter sort of 30 years ago, but sort of one can measure very accurately those magnetic fields, and one can also predict them. One can use linear response theory to predict what is the induced current, what is the induced magnetic field, and thus calculate the magnetic shift. And in this case, this was used to show that one can differentiate very clearly the configuration of borocarbene structures, where otherwise you would have no other technique to understand how the, say, black atoms versus respect to the gray atoms would arrange themselves into this icosahedra. Okay, I already told you that one of the first things that we want to do using this complexity, the capability of calculating forces, the capability of calculating response properties, is to describe materials at certain given thermodynamic conditions in a given ensemble. And the most important thing to understand is what is the effect of temperature on material properties. And temperatures means that we are exciting the possible degrees of freedom. I've already told you very briefly, we'll see it in a moment much more accurately, that one could excite the vibrational degrees of freedom. But other degrees of freedom that are important are maybe the magnetic degrees of freedom, that would have to do, say, with the Curie temperature, how a ferromagnetic material transforms itself into a paramagnetic material. Could have to do with the vibrational contribution from the occupation of states, or a very important, say, in an alloy, it would have to do with the different possible configurational degrees of freedom. And you might understand that these two microscopic representation of black and white atoms, might lead to very different entropic contribution in addition to very different energetic contributions. And say in a strand of DNA, in a protein, also in polymorphs, there are more delocalized conformational changes that are also very sensitive with temperature. When you take your egg and you sort of cook it, you are basically denaturating the protein. So you are, pushing some irreversible changes in the quaternary structure of the protein. So for this, I taught you quantum mechanics on Wednesday in 5 minutes. I'll teach you statistical mechanics in 30 seconds. Basically, in statistical mechanics, what you need to do is you need to understand that every microscopic state has a certain probability. This is the fundamentals idea coming from Boltzmann, that is proportional to the exponential of minus beta is the inverse temperature times its energy. So the lowest the energy of a state is, the more likely it is to be. Now, calculating this probability seems easy, the exponential of minus beta, the energy. What is difficult is calculating the normalization factor for that probability, because those probability need to sum up to 1. And that normalization factor is what is called the partition function, that is the sum over all the microstates, sum over I of all the Boltzmann factor. And because you typically have an exponential explosion of all the possible microstates that are consistent with your thermodynamic condition, think at a piece of aluminum at room temperature, the atoms are not going to stay in the equilibrium perfect position of a Bravais lattice at 0 temperature. They're going to vibrate around, but having one vibrate a bit more and two vibrate a bit less is equally good if the total energy of the system is the same, and there are an enormous amount of ways by which this happens. So calculating this Q is difficult. If you are able to calculate, I will see in a moment a case where you do it, analytically you can get right away the free energy, the Helmholtz free energy minus Ts from the logarithm of that partition function. There are very few physically relevant examples where we can do this analytically, but vibrations in solids is a very beautiful example, because at low temperature, that is in the regime where those Phonon dispersions are well defined with very sharp lines with very small line widths, what we can think at is our system being made by a collection of harmonic oscillators. And so for every Phonon branch, so the 6 Phonon branch here of diamond would be labeled with J, and for every block quasi-momentum wave vector q. So for every point in that, you remember we had this Phonon dispersions. So for every point in those dispersion, J and Q, what we have is a harmonic oscillator, and the spectrum, the quantum mechanical spectrum of the harmonic oscillator is given by the harmonic frequency, the classical harmonic frequency omega times h bar, and all the excitation go with n equals 0 is the ground state, so the 1/2 h bar omega is the 0 point configuration, and then we have 3/2 h bar omega, 5/2, and so on and so forth. And as I've already told you, the partition function of, say, one harmonic oscillator, so for a given J and for a given Q, is obtained by summing over all possible microstates, so summing all over summing all over all possible energies, summing over all n, the Boltzmann factor exponential of minus 1 over kBt times the energy, and the energy is, you see, h bar omega times n plus 1/2. So this sum, luckily, can be done analytically. It's just a hyperbolic sign, so it's what I've written here. So this is the partition function, the sum over all microstates for one harmonic oscillator. And in the solid, we have main independent harmonic oscillator, an infinite number. Let's say that approximately we sample it, so we just have to take the product of this partition functions. And this will give us the vibrational entropy. If we take minus kBt, the logarithm of this partition function, will give us the vibrational entropy of my solid. So we discover something very important, that is, I know already how to calculate the energy of a solid. For reasons that will become clear in a moment, I've written it as a function of the lattice parameter. But if I know how to calculate phonon frequency, I know also to calculate the Helmholtz free energy. I know how to add to my energy the vibrational part, where there is a 0-point motion contribution and there is a temperature-dependent contribution. Now, I've calculated this expression, and now what I could say is, what happens, say, to the lattice parameter as a function of temperature? I've already learned that the lattice parameter as a function of temperature is the minimum of the potential energy surface. So at 0 temperature, it would be the minimum of this. Now, at finite temperature, I discover that my energy becomes the free energy, and I have an additional term. How do I calculate the minimum of this thing? Well, the simplest way is considering that the phonon frequency will depend on the lattice parameter. And the same here. That is, if I expand my solid or I compress my solid, the phonon frequency will go up or down. If I expand it, they typically become soft. If I compress it, they typically become harder. That's not always true. If I take a piece of graphene, say I take a 2D or a 1D material, I take, let's say, a nanotube, and I stretch it, actually the most important frequency go up. And that's, you know, what happens like to a string in a guitar. If you sort of stretch the string of a guitar, the frequency goes up. But say in a piece of silicon, if I stretch it, I'm mostly weakening the bonds and the frequency go down. But the important thing is that I can calculate this phonon frequency as a function of lattice parameter. And so I can also calculate what is the dependence of the vibrational entropy as a function of lattice parameter. And so I can do a calculation of, say, not the energy, but the free energy as a function of lattice parameter, say at 0 temperature, and then at other different temperatures. And you see I have logarithm of 1 minus something that is between 0 and 1, and so the free energy is going down. And in this case, the lattice parameter is, you see, increasing. And not only, this curve is shifting, but it might also be changing its curvature. In a piece of silicon, in a piece of diamond, it would typically become shallower, so the second derivative would become smaller, so the bulk modulus, that is that second derivative, would become softer, and lo and behold, this is exactly what we see. That is, if we compare the temperature dependence of the bulk modulus as it is measured in experiments, this blue little, now they are becoming red, this blue little symbols, and I compare it with what I calculate, you see that the agreement is actually extremely good. And the reason why we get, forces and phonons very, very well with, PBE, while formation energies were much more difficult, is that there is a lot of cancellation of errors in, say, in calculating a harmonic frequency. I'm shifting the atoms a little bit from their equilibrium position. And so what I need to describe well is that change. Maybe the ground state was not described super well, but if I can describe well the change from the ground state under that little perturbation, I can actually do quite well, even if the ground state was not done very well. So formation energies, where we compare ground states that are very different, in lead titanate, the titanium is, in a 4+ state, while in titanium metal, it is a 0 oxidation state. Its bonding and coordination has changed a lot, and all those errors I pay. If I calculate the phonon dispersion of lead titanate, I do a very good job in the ground state at 0 temperature, because exactly I have to calculate these second derivatives. And here I've been a little bit smart, or maybe not completely fair, because I've not plotted the absolute value of the bulk modulus calculated with respect to the absolute value of the bulk modulus that has been measured. There would probably be a 10% difference. You remember, volumes, come out wrong by 2, 3, 4, 5%. Elastic constants can easily be wrong by 10, 20%. But what I'm plotting here is the change in temperature of the bulk modulus with respect to the bulk modulus at room temperature, where in the solid red and black line, the reference is the GGA bulk modulus at room temperature. So it's 1. You see, it's this point here. I've taken this as a reference. These two curves would not be the same if I had looked at absolute numbers, but now I'm looking at the change with respect to the reference number, in this case, the calculation at room temperature and the experiment at room temperature. So this was an example where we can do thermomechanics of materials analytically using our capability of calculating partition function exactly. In most times, we are not able to do that. And so if we wanted to calculate what is, say, an average property in a given thermodynamical ensemble, we need to do thermodynamical averages. And this is the classic definition. So again, I need to take my observable A, and for each microstate, define in this case for a dynamical system, let's say this is just one particle for a certain set of positions R and momenta P. And this is that I've plotted here on the right is the phase space of position, and momenta is a generalized one. So it would be in 6 dimensions for one particle, in 12 dimensions for 2 particles. But I have to do that integral. And for every point in that phase space, I have a given position, I have a given momentum. So I know what A, that is a function of R and P, is. I weight it with the Boltzmann factor, I divided it by the partition function, and I'm done. I'm done is ambitious because doing integrals in multi-dimension is incredibly complicated, because every time you add 1 dimension, you have 1 more dimension to integrate. So again, it's a exponential complexity that kills you it's exactly like the wave function, 10 to the third, 10 to the sixth, 10 to the ninth, and so on and so forth. But there are very smart techniques that we'll look at in a moment to do that, and those are the molecular dynamic approaches and the Monte Carlo approaches. The molecular dynamic approaches are easier to understand, and we are now in a classical world. We will not use quantum effects, so our atoms are moving around as classical particles with the mass in the nucleus, carrying around the electrons in the adiabatic approximation, always in the ground state. And suppose for a moment that this figure represents maybe a protein folding. So I might have tens of thousands of atoms, and the phase space is 6 times that. So I am a point in this, let's say 100,000 dimensional space, and the evolution of the protein in that phase space is a trajectory that maybe after a while, this is a very unlikely protein, maybe it's some kind of kinesin or some kind of molecular motor, but after a while it starts running over those loops. Well, we can translate, say, the language of thermodynamic ensemble averages in the language of averages over a trajectory, and that is done under what is called the hypothesis of ergodicity, that is saying that the temporal average, okay, this is what this integral is the time average over a long time t of my observable, that it's a function of r and p, but now it's become a trajectory, so it's a function of time. So the average in time of what a is at every instant during the trajectory, so this a bar is equal to the ensemble average. And this is really because in my trajectory, what happens is that these points along the trajectories are going to be weighted with relative weights that depends on their Boltzmann factor normalized by the partition function. That will become clearer as soon as we do the Monte Carlo method in 3 minutes. And so what I can do then is average over a trajectory rather than an integral over phase space. And that's much, much easier to do because I can evolve my system using molecular dynamics, treating it, as I said, the nuclei as classical. This is what we would have for a single atom. In reality, we have a set of coupled Newton equation of motion, one for every atom, where the force is the Hellmann-Feynman force that comes from DFT, if we want to do, let's say, first principle molecular dynamics. And the integration of this equation of motion gives me, say, a trajectory, position as a function of time, and velocity as a function of time. So what we need to know is what is the Hellmann-Feynman force for every configuration, and then we integrate this equation of motion. How we do that? There are many ways. A beautiful and very simple one is the one that was developed by Verlet, developed a number of algorithms. This is called the simple Verlet. And it says, well, if we have the position of an atom at a certain time t, it's very easy to understand what would be its position at a next time step. So think of this as a frame in a movie, t plus delta t. And what I do, I just need to do a Taylor expansion. So this is a Taylor expansion of the position trajectory. So r at t plus delta t is equal to r at t plus the first derivative of r with respect to time, that's the velocity, times delta t, plus the second derivative of r with respect to t, that's the acceleration, 1/2 in the Taylor expansion times delta t squared, plus 1/6 the third derivative, plus 1/24 the fourth derivative, and so on and so forth. But I can, expand both forward and I can also Taylor expand backward. And so if I do the same, what I have is that the odd terms have the opposite sign. So they have a plus and a minus, and the even terms have the same sign. Now I can take the sum of these two quantities. So if I take the sum of these two quantities, you see I've got the R t plus delta t is equal to R of t plus R of t, 2R of t. These two terms cancel out. These two terms cancel out, and that's very important. This term here gives me acceleration times delta t squared, and then I have this term on the right side now. So the simple Verlet algorithm tells me that the position at the next instant, t plus delta t is equal to twice the position that I had minus the positions that I had the instant before, plus the acceleration that I have, and the acceleration is given by the force divided by the mass times delta t squared. And because the first order and the third order terms have cancelled out, the errors that I have are only in the fourth power of my discretization, and so they can be very, very small. And if I make my discretization, twice as small, my error becomes 16 times smaller. And so with this, I'm actually able not only to shoot cannonballs, but I'm able to send people to the moon. If you look at the codes of the Apollo program, that were developed in the, I think in the, whatever was called the research laboratory at MIT, in the 60s, by a woman. Today is not a good day, Margaret, I forgot her name, I apologize to her. But there are beautiful pictures of her with just this pack of code that she had written. You can find out the Verlet algorithm that was used to circulate around the moon. And because the moon is not really homogeneous, there are gravitational anomalies, it's very important to send unmanned probes before to check for those gravitational anomalies and to put a few correction terms. But now that I have, a way to integrate the equation of motion, so what I can do is take, a very complex system. I can take, a large unit cell filled up with water molecules in periodic boundary conditions, so they don't feel the presence of a surface, but a supercell large enough so they don't feel each other. And remarkably, having a few tens of water molecules at room temperature and that, the current sort of ambient volume is enough actually to reach the bulk thermodynamic limit. And then I can integrate the equation of motion for all these objects. I can measure what is the kinetic energy of these molecules. And if it's not what I want, maybe I want to simulate this at room temperature. There are techniques that I won't go into. There are thermostats that can decrease or increase the average temperature of these molecules. And once they have reached the average temperature, I can measure physical quantities that I'm interested into. And you have examples here on the right of pair correlation function. A very interesting one is the oxygen pair correlation function that tells me what is the probability of finding an oxygen at a certain distance from me if I myself am sitting on an oxygen atom in one molecule. And you see the probability of finding an oxygen very close to me, less than 2 angstrom, is basically 0, because there is my charge density. There are my 2 protons, so no other molecules can come close, but around 2.3, 2.4 angstrom, the probability of finding another oxygen is very large because there is the first solvation shell of the 4 water molecules surrounding me. And if I go a little bit further, the probability of finding an oxygen decreases because that first solvation shell is stopping other water molecules that arrange themselves around the second solvation shell and the third solvation shell, and this pair correlation function far away becomes flat because the probability of finding an oxygen 1 kilometer away from me or 1 kilometer and 1 angstrom away from me has become the same. And as you see, if we do a classical molecular dynamic simulation with forces that are obtained with a state-of-the-art Born-Oppenheimer, sorry, the state-of-the-art van der Waals exchange correlation functional, we actually do a very good, job. If we start looking at something a little bit more subtle, like the oxygen-hydrogen or the hydrogen-hydrogen pair correlation function, or here they're called radial distribution function, we start seeing that the agreement with experiment is less good, exactly because, as I told you the first day, the protons in themselves, even if they are 1800 times heavier than electrons, have some quantum effects that take place in the form of Bose-Einstein statistics for the vibration excitation and the capability of tunneling. And to do that, it's something that can be done. You can do averages taking into account this effect. Those are called path integral molecular dynamic simulation. Very, very expensive. So in this example, it was very difficult to do them directly on density functional theory calculation. So they fit a neural network on the density functional theory calculation to get the trajectories, and then those trajectories are fed into the path integral molecular dynamics. But when you do that, the solid red and the solid black seriously agree with each other. That means that we are describing the structure of water very, very carefully. Not only that, but we can use these molecular dynamic techniques also to study events that are taking in real place. So this is actually the chemistry of a methane molecule dissociating over a metal surface. This is with high impact energy. So actually hydrogen is ripped away from its carbon-hydrogen bond by the uncoordinated platinum. So here we are not calculating an ensemble average, but we are looking at a molecular dynamic simulation in real time. Okay, I suggest that we stop for everyone to recover a little bit for 5 minutes, and so we'll start again in 5 minutes sharp. Okay, welcome back, and let me discuss the other way by which we can sample thermodynamic ensembles. Again, what we have to do is go back and think at the way the expectation value is written in the language of statistical mechanics. And as we said, there's integrals, multidimensionals would be very difficult to do. One way has been using the ergodic assumption to sample along trajectories points that are distributed according to the Boltzmann factor divided by the partition function. And the beauty of that is that that transform this expectation value in just the average 1 over n of all the values that are measured. So one way to do that, alternative to molecular dynamics, is the one of Monte Carlo sampling, where one can build different algorithms that allow me to walk around that phase space where I had before drawn that black and red trajectory. So I can walk around phase space with choosing microstates that on average are distributed according to the properly normalized Boltzmann factor by the partition function. And one way that is very popular is been developed by Ariane and Marshall Rosenbluth, and the head of the group was Nicolas Metropolis, and so it's called the Metropolis algorithm, but he didn't do anything. And basically what it entails is making changes in the configuration of my system. I'll show you an example in the next slide. And I change the configuration of my system. It could be, say, if I want to try and replicate what molecular dynamics does, it could be moving an atom a little bit. And if the energy of the new configuration is lower than the previous one, I accept that configuration. And if it's higher, I don't reject it, but I accept it with a Boltzmann factor that is proportional to the energy difference. And if I do that a lot of times and in the appropriate way, what I generate is a Markov chain, is I generate a series of configuration in a phase space that are distributed according to the correct thermodynamic ensembles. It could be, say, at a given volume, at a given temperature. This is called important sampling because it's a technique that allows me to sample only the important point. Here is a cute example taken from the book of Dan Frankel and Berend Smith. Apologies to Berend for the H here. So, you know, one example is, you know, what is the average depth of water in the Sahara? Let's say that we focus for a moment just on the Sahara. So if you were to do, say, just the integral discretized, what you would do just these points. So at every point, the depth of the water is 0. You would never hit the Nile. And so no matter how fine you are, you have never measured, you have never found the Nile. So your average water depth is 0. If instead you have a technique that brings you to the Nile, and when you are in the Nile, it makes you stay there, because every step that you take, if you go, you know, deeper in the Nile is kept, and if you go shallower in the Nile is kept only with a certain probability to depend on temperature, allow you to spend, you know, most of your time in the interesting part of phase space, and that is to sample the Nile very, very carefully. One example, and this is really a trip down memory lane, that puts all of this together, and I'm afraid is almost 30-year-old, and is really using these ideas to calculate the phase diagram of a substitutional alloy. Here we have a 3,5 semiconductor alloy, something where the black atoms, the anions could be, say, phosphorus or arsenic, and the red and blue, the cations could be, say, gallium or indium. And what we need to do is to be able to have the energy from density functional theory of a given configuration. So if you only needed, a few tens, a few hundreds, even a few thousands of configurations, configuration is a system in which, I have an arbitrary choice of red and blue atoms on those substitutional crystallographic position. Well, I could do brute force DFT, but in reality, I needed to do good thermodynamical averages with millions of configurations. So I cannot do it by brute force DFT, but I can model the energetics of the Hamiltonian in some of the different ways that have been developed by the communities in the 80s. There are ideas like cluster expansions, or there are ideas related to density functional perturbation theory that I show here, in which we actually, consider a red or a blue atom, a gallium or an indium, as made by an average atom, that is exactly the average of the pseudopotential, so the green atom, plus or minus the semi-difference of the pseudopotential. And if the two atoms are chemically very similar, the semi-difference is very small, so we can use a perturbation theory, and using all these ideas that we have seen before for phonons, we can expand the energy up to the second order, not in the displacements, those would be the phonons, but in the configurations. And those interatomic force constants, phi, now become these chemical force constants, J, that tell me what is the change of energy for a given configuration up to the second order. There are more subtle issues here related to the fact that atoms will relax, but that can be taken into account. But what perturbation theory gives me is an energy model that is completely inexpensive. If I've calculated the J once for all and the K once for all, the sigma just +1 or -1, because adding or subtracting the semi-difference of the pseudo potentials. And with this now I can do Monte Carlo simulations. And in particular, I can do Monte Carlo simulations in a thermodynamical ensemble in which I vary the difference in chemical potentials between, say, the gallium and the indium, the blue and the green atom. So if that difference is very, very low or very, very large, very negative or very positive, the concentration of the alloy that I measure if I do a long Monte Carlo simulations, that is, I keep swapping a red and a blue atom, I make a red become blue, I make a blue become red, I keep doing it, and I do it millions of times. Every time the energy goes up or down. If it goes down, I accept that configuration. If it goes up, I accept it with a Boltzmann factor in the difference of the energy. And I do it many times. I take the average concentration, and after many, many trials, I will have converged my average concentration X for a given temperature and for a given chemical potential difference. So every point here is a Monte Carlo simulation, and these curves give me the dependence of the average concentration as a function of chemical potential difference. You see, if the temperature is very, very low, this is 650 Kelvin, but suppose I was at even lower temperatures, it would be almost the Fermi-Dirac distribution. If the chemical potential is low, I am all gallium phosphide. If the chemical potential is high, I am all indium phosphide. And if I start to have a temperature, the discontinuity becomes smoother. And these curves that represent the, say, concentration as a function of the chemical potential difference can be inverted. That is, I can get the chemical potential as a function of the concentration. And since that the chemical potential is given by the derivative of the energy with respect to the number of variables, and I can integrate that, I can get the free energy. So by integrating these curves, I can get the free energy of the system. I can do a common tangent and say this is for the curve at 600 Kelvin. What I see is that, there are stable concentration at 0.1, let's say, and at 0.85, and anything in between, what I see is that the mixed system has a free energy that is higher than the energy that I would have if the system at this concentration were to decompose according to the level rule into two subsystems, one reaching one species at that concentration that is the minimum of the dip on the left, and at the other concentration on the right. So anything in between, so I am at 650 Kelvin, so the 2 points I've drawn are here, so anything in between here is inside a miscibility gap. The system doesn't want to stay mixed, but wants to separate at this concentration here, so into two subsystems. And there is even a spinodal in here that is delimited by the inflection points here, where inside the spinodal the system is not only globally thermodynamically unstable, but is unstable also with respect to a microscopic change in concentration. So you see, even 30 years ago or 25 years ago, we could do very sophisticated phase diagram, in this case of semiconductor alloys, using model Hamiltonians that one can build a fitting on configuration. These days you could do neural networks, so you can do, in this case, use density functional perturbation theory, and then use Monte Carlo techniques to sample the thermodynamical averages. So this was an example of properties in different thermodynamic ensembles, especially temperature is important here. Temperature affects the entropy and the configurations. So you have seen the case of molecular dynamics, you have seen the case of Monte Carlo. Now I want to go into even more complex properties. This is one of my favorite. It's looking at transport. Transport could be electrical transport or heat transport. Electrical transport comes from the fact that, say, in a perfect crystalline solid, conductivity is limited, the current is limited by the fact that electrons interact with vibrations, so there are electron-phonon interactions. Heat transport is limited by the fact that vibration interact with each other. There are, of course, other scattering mechanisms. If there are impurities, if there are grain boundaries, these would all be relevant. Here I'm talking about intrinsic mechanisms, and you can actually calculate what are the probability, say, for a phonon to, in this case, decay into two phonons, or maybe for two phonons to coalesce into one. This can be done, I'll show it in a moment, with Fermi-Golden's rule, and you can do the same for electron-phonon interactions. All of these scattering rates require the calculation of the third-order derivatives. There are, in the language of second quantization, three phonons interacting, or electron and phonons interacting. We get from third-order density functional perturbation theory the scattering rates, and from the scattering rates, so this is why it's a multi-scale multi-physics, we can integrate Boltzmann equation for the populations of electrons or for the population of phonons. And if you do everything by the book, you calculate phonons from density functional theory, that is good. You calculate electronic bands from GW, from many-body perturbation theory, and you put this together to calculate this scattering rate. In many cases, you have to do very, very accurate integration on the Brillouin zone, that are done doing electron phonon interpolation here with the EPW code, and then you solve the Boltzmann equation. The results can look like this. That is very good. This is the resistivity of a monolayer of graphene as a function of temperature and as a function of doping. This is the experiment done by Philip Kim in 2010 when he was still at Columbia. And this is what, on the left, what you obtain with the first principle calculation. So in general, very, very good agreement with experiments. And you can also go beyond what maybe experiments are measured. Since you believe the calculation at low temperature, you should believe them also at high temperature. And you see that the dependence on doping saturates at high temperature because the conduction mechanism and the phonon involved change, the dominant player change. Again, without going too much into the detail, I just told you that you can calculate this probability with a Fermi golden rule. I show here for the case of 3 phonons, either for a decay process, 1 phonon decaying into 2, or 2 phonons decaying into 1. And you see the key ingredient are conservation rules on the frequency. So you need to know what are the second order derivatives, what are the vibrational frequencies, and the amplitudes, the third order derivatives are gauging this line width, that is nothing else than the scattering rates. And so these third order derivatives are calculating using density function perturbation theory and the 2n+1 theorem to give me, say, the line width, and the inverse, that would be the lifetime of the phonon. And that is how long a phonon excitation lives before it, say, decays into 2 excitation or coalesce with another phonon to give a third phonon. And of course, there can be 4 phonon processes, 5 phonon processes, is that those are progressively less and less likely. So here we are looking at the first important intrinsic scattering mechanism that happens already in a perfect crystal just because there is a temperature. And if you look at this lifetimes, you can actually solve in closed form the Boltzmann equation, the linearized Boltzmann equation, in a certain approximation that is called the single mode relaxation time approximation. That's an approximation that says that phonons do not repopulate other phonon population. That is to say that the scattering mattering is diagonal. Doesn't really matter, but just to give you the flavor of this, thermal conductivity, there is a 1 over square root of the temperature here, but the other quantities are the phonon frequency that you know how to calculate, the phonon populations that are the Bose-Einstein population on these phonon frequencies, the group velocity squared that are just the derivative of this phonon dispersion, and the lifetimes that we can calculate with third order derivatives, as I just shown in the previous slide. So if you calculate all of this from first principles, maybe in a perfect solid, the next example shows what happens actually in an alloy where we put through the Mathieson rule the line width not only for the scattering but also for the isotopic disorder, and what we get is the black curve that is actually in very, very good agreement with experiments. And you see this very sudden drop in a silicon germanium alloy. That's true for alloys in general. 1 order of magnitude with just a few percent of germanium comes because as soon as you have a little bit of germanium, you have many more possible vibrational frequencies. So those conservation rules in the 3 phonon processes that we had here can be satisfied in many more ways. So the line width becomes large and the lifetimes becomes small, and the thermal conductivity become small. I realize I'm showing you a lot of examples of computational material science done by myself and the group. The reason is probably just because I love them and because I'm much more familiar, but if you just search the literature, there is a wealth of properties that can be calculated. And actually, Springer has published in 2005 the first edition and just now the second edition of the Handbook of Materials Modeling that really gives you a bird's eye view on everything that can be done with simulations. One thing, and this is just one slide that is dear to my heart because we just showed last year that actually Boltzmann transport equation was missing an important term. When the line widths of the phonons become large, a phonon wave packet can tunnel from one branch to another. And that's a mechanism that is almost irrelevant in a piece of silicon or a silicon germanium alloy. That is what is described by the so-called Piles theory of Boltzmann transport, but it becomes very relevant in materials that are very anharmonic with large line widths, materials that have many phonon branches that can talk to each other, or in the limit of amorphous or glassy system. And we call this additional term, this tunneling term, coherences. And you see quite beautifully here in one of these metal organic perovskites, we have that the thermal conductivity that we predict is this, I would say in very good agreement with experiment, but the Boltzmann equation would give you this term here, even with the wrong asymptotic decay with respect to temperature, and the tunneling term becomes important already at 100, 150 Kelvin. At room temperature, it almost dominates, but is essential to get the right results. An example from the literature, very beautiful, from the group of Francesco Mauri. You probably have heard of the world record experimental in superconductivity in lanthanum hydrides at very, very high pressure, 250 Kelvin. That is just, 40 Celsius below freezing. So it's, it's ambient temperature in very cold places. It's not ambient pressure. The beauty of this is that these systems are very, very anharmonic. So you can calculate actually superconductivity from electron-phonon interaction and from the so-called Migdal-Eliashberg formulation, is that the system is so anharmonic and its line widths are so large that you can't just use a second-order perturbation theory to calculate the vibrational frequencies. You need to take into account a higher-order effects, and that is done in this paper with fairly sophisticated way to sample the phonon self-energies, but they get basically the right phonons, the right electron-phonon interactions, and at the end you see how beautiful this is the curve that they get, the solid thin red line for the superconducting transition temperature as a function of pressure, in general, in very, very good agreement for such a complex system with experiments. A few other examples of material properties. This is one that I love. It was a project here with the watch industry in Switzerland, calculating the colors of novel metal alloys. And this is actually, it's fun, but it's also a lot of physics because what we have is a photon impinging on a metal. And so what's happening is that we are exciting electrons with transition between the bands, transition within the same band, plasmons, and we need to understand all these transitions to calculate the dielectric response in the optical limit, in the long wavelength limit, because the photons don't carry any momentum, but any frequency at any frequency, and that gives us the reflectivity and the absorption of the material. So it tells us how shiny it is and what is the color, and we know what is also the spectral response of a retina to light that was coming with solar spectrum, is absorbed and reflected by the metal. It's captured by a retina, and if we know what is the solar insulation, we calculate what is the dielectric response of the metal. We know what is our sensitivity. We can figure out what's the color of the metal, and again, you see it just graphically. Theory and experiment work very well. One last example again of a multi-scale, multi-physics simulation, that is electrochemistry, where you're looking at a chemical reaction taking place at an applied electrochemical potential. And so what you have, maybe this is, carbon monoxide that's stored on platinum. What you're doing with your leads, you're charging your system. So charge will accumulate or deplete at the surface. The solvent will respond to the electrolyte. Maybe you have some sulfuric acid dissolved in there. It will rearrange itself, and you can study this with quantum mechanical simulations by taking into account how the quantum mechanical system responds. So this is like a generalized Poisson equation in the presence of a solvent, in the presence of an electrolyte, in the presence of charging, and you can study, say, how the vibrational frequency of this carbon monoxide would change as a function of potential, the Stark tuning, or you could study how the free energy of the adsorbate would change as a function of the electrochemical potential. And so you can understand what is the concentrations of adsorbates at the surface. So in turn, what is the free energy of that surface? And so in turn, what would be, using the Wolf construction, what is the surface orientation the system wants to expose as a function of applied potential. Here we are technically in the regime of under potential deposition for platinum nanoparticles, and you see what's happening in the system is that the 1-1-1 orientation has a strong pH dependence, because the 1-1-1 orientation is very packed. So having or not hydrogen on that changes a lot. The dipole changes a lot how it couples with the electrochemical potential, and the 1-0-0 is less affected. But in general, we are getting to the stage these days where we can do electrochemical calculations. So let me conclude the part of application with one example. Again, I double apologize because it comes from our work. It's because I'm very fond of it. It's an example of high throughput calculation. That is an idea, very beautiful, that was introduced first in 2000 by Carsten Jacobsen and Jens Norskopf to look at catalysis on quaternary alloys, at least in the field of ab initio calculation, and by Gerd Seder and Stefano Curtarolo at MIT to look at inorganics and then to look at battery cathodes. And similarly, other ideas came from Alex Zunger about inverse design. So this is by now very well established. This is just an example that has been a lot of fun for us in looking at inorganic materials that could be peeled off into monolayers, exactly as experimentally Gaiman and Novoselov have done with Scotch tape, peeling monolayers of graphene from graphite. And so this is typical for this high throughput project. It's very common. We take databases. Here we have experimental databases, but they could be computational databases. And we screen those to see if there is something interesting. Here, the screening criterion is to see if these materials are layered. And if they are layered, we calculate a lot of basic properties, electronic magnetic properties, and then the properties that we want to screen are these monolayers with high mobility and a good band gap that could, say, work well for maybe short channels, field effect transistors. And we do this in a high throughput mode. Actually, we develop all the workflow technology and workflow engine into AIDA that allows to do this in very repeatable, reproducible, and traceable ways. And then for this particular project, we have looked at many properties. One that has been a lot of fun was looking for novel topological insulators in 2D, quantum spinol insulators. And we find a mineral that was discovered in Brazil in 2008. It's called jacutingate. And if you do actually an accurate calculation of their electronic state, not with density functional theory, but with many body perturbation theory, with GW, with spin orbit coupling, that is very important in this topological insulator, well, you discover that actually Jacutingite is a quantum spinol insulator with a huge band gap, half an electron volt. This is enormous, it's room temperature topological insulator, and actually it's the first ever discovered that displays what is called the K-Melee physics of spin orbit coupling. That's very technical, but we just have some very beautiful results in ARPES on the topological structure of the bulk material. We don't have a monolayer. We do not have a monolayer yet, but we have the bulk. And you see for the bulk, even the DFT band structure on the right is good, and it reproduces very well what is measured in angle resolved photo emission experiments. Okay, with this, I hope I've given you just a little flavor of what can be done. This is the field of computational material science, how we take density functional theory and we calculate interesting properties with it. Let me actually conclude this presentation saying, you know, what's actually wrong with density functional theory, in which sense it is approximate, and where are those approximations, you know, harmful to what we want to calculate. You have already seen that, you know, in general, it tends to be very good to predict, say, structural properties of materials, even van der Waals bound materials. Formation energies are a bit more challenging. Band gaps are completely outside of the scope of density functional theory. So, you know, when I say what is wrong is that sadly we don't have the exact functional, but also there are properties that go beyond the density functional theory. The fact that it's a function of the charge density means that we can calculate exactly the energy and its derivative, the response function of the energy, but we cannot calculate other properties like excitation. So we cannot calculate, say, what is the band structure of a material. So here is a summary of things that go wrong either conceptually or in practice. This is an interesting example, is the ionization potential of atoms. I'm plotting the experiments in red, and I'm plotting the ones that is calculated in LDA. And you see the differences of the order of a few or even tens of electron volts. Now, when I say the one calculated in LDA, I mean as calculated from the HOMO. I told you that Kohn-Sham states are meaningless in density functional theory, but that's not completely true. The highest occupied orbital determines, just by the nature of the differential equation, in a molecule, what is the decay at very, very far distances from an atom or from a molecule of the charge density. And we know that in exact density functional theory, the charge density is going to be exact. So in exact charge density, in exact density functional theory, the Kohn-Sham HOMO is exact, and it should match the experiment. The fact that in LDA it doesn't match it, it's unfortunate, but it's what it is. It tells you that actually that energy level is very, very far away from experiments. So the decay of the charge density actually in the atom, it's only a tail, so it doesn't really matter that much, but is asymptotically wrong. Of course, you could actually calculate the ionization potential with two calculations in this case. You could take the atom and the atom without an electron, and from these two total energy differences, you would get probably a very good ionization potential. But here we want to talk about the spectrum of the atom, where that HOMO lies, and that HOMO in LDA lies in the very wrong place. The LUMO, even worse. And this is very important for something like this. This is another molecular dynamic movie. It's 25 years old, so that's why it's very coarse-grained. It displays a chlorine molecule falling on an aluminum surface. It's one of those harpooning processes that I show in the first day. So as the chlorine comes closer to the aluminum, the LUMO of the chlorine molecule starts to be degenerate with the work, the Fermi energy of the aluminum. And so you have the transfer of actually 2 electrons from the aluminum to the chlorine. And that happens when the chlorine is still far away from the surface. So the 2 electrons move into the chlorine explodes. It's what we call a cannonball dissociation. Sorry, the movie, that's why I started late. The movie was not working, it's not working. So I'll do the movie myself. The chlorine comes down and it explodes in 2 atoms that run very far away from the surface. Now, the problem here, it's very interesting. The issue is that in exact DFT, this simulation should be exact because we are moving slowly. So we are following, the adiabatic crossing and the charge transfer. The issue is that in approximate DFT, the LUMO is in the wrong position. It's much too low. And so as it comes closer to the surface, it lowers even further, and it feels the presence of the Fermi energy much earlier than it would do in real life. So you have the charge transfer when the molecule is still quite far away from the surface, and that's why it explodes, because it harpoons the electrons while it's not bound to the surface, and it becomes at Cl2 minus, it doesn't want to stay bound together, and it explodes while falling on the surface, and they end up very far away. But that is true in the LDA simulation. It would not be true in real life. What would the exact DFT do? Well, also in exact DFT, the LUMO is in the wrong place. So what happens is that as soon as the LUMO starts becoming degenerated with the Fermi energy, it becomes infinitesimally populated, and so it becomes the HOMO, and the HOMO is right in exact DFT, and so it moves actually up and it becomes empty again. Of course, this is all differential analysis, so it's not that it happens in practice, but this is just to say that what you are seeing here at place is the effect of the derivative discontinuity in the SD functional theory. That is, there is a finite change in the potential that is felt by the LUMO when it becomes the HOMO. And because we are not describing it correctly, we are not describing the process correctly. Other examples, this is a model dimer, something very simple where one can try to do in different ways using the so-called Schramm-Schluter equation, estimate what should be the exact exchange correlation potential for a dimer. This is a monoatomic, so it's a simple model, but it captures the physics very interestingly. I'm separating these 2 atoms, this lithium and this hydrogen, and this is the distance. So 10 corresponds to lithium and hydrogen very far away. And you see what happens to in particular to the exchange correlation potential. It grows an iceberg in the middle of where the lithium and the hydrogen are not. And this iceberg is really built to make sure that we don't have the incorrect charge transfer because of the wrong position of the orbitals that I was describing before. But this iceberg is growing where there is no charge density. So you understand how difficult and how non-analytic the exact exchange correlation potential is, that has to grow real large things in places where there is infinitesimal charge density. Another example, this comes from the binding of, these are thiophene, thiophene. So each of these molecule is given by 3 thiophene rings. It's like benzene, but with 1 sulfur. And it turns out that a dimer of thiophenes is actually bound when you oxidize it. That was at the time was a very fun project in trying to build a molecular motors where you had a hinge that was keeping 2 thiophene opening and closing depending on their oxidation states. Well, if you do a LDA calculation in this system, what you get is, you're oxidizing the system, so you have a hole. If you had only one thiophene chain, what you would know from high accuracy calculation is that the hole would be localized in the center of the molecule. In reality, the hole is delocalized onto the entire molecule, and when you bind them into two, is delocalized over both molecules. Is exactly what I am representing here. This is the delocalized hole in DFT, GGA, that is not exact, and we know instead that the hole should localize itself only in one of these two chains and just in the middle of it. So completely qualitatively incorrect description of this hole that maybe not for the binding, that would also be incorrect, but for the transport properties would be fundamental to describe correctly as a localized polaron hopping. And this is my last example, my favorite example, and I'm looking at the simplest system possible, simplest molecular system possible. It's a hydrogen molecular ions, H2+. So you have two protons here in blue with +1 each of them, and I have one electron in red. And I'm looking at what happens when I dissociate this molecule. So in exact quantum mechanics, if I dissociate this molecule completely, the two protons are very far apart, I have degeneracy. I have left-right degeneracy. That is, I can have one proton with one electron here on the left and another proton on the right naked. So I have a hydrogen atom and a proton, or I can have the vice versa. So those are two degenerate states, and because they are degenerate, any linear combination of these two states is degenerate. So exact quantum mechanics for this program tells me that the electron can sit on the left, the electron can sit on the right, can sit 50-50, 20-80, 10-90, any linear combination. And the energy of all these configurations is the same. I do an LDA GGA calculation. What I discover is that instead, in my dissociation of the molecule, half an electron sits on the left and half an electron sits on the right. This is because the Hartree term is dominating over the exchange correlation term because of the way our approximate exchange correlation is. And so the Hartree self-interaction energy wants to spread out the electron as much as possible, and so the best possible configuration is half and half. And the exchange correlation potential is not canceling out exactly the Hartree potential as Hartree-Fock would do for one electron. Remember, the exchange term for a one electron case cancel out exactly the Hartree term. The Hartree-Fock equation becomes identical to the Schrödinger equation, so Hartree-Fock is exact for this problem. It's when you have many electrons that is not so good. Kohn-Sham, that is quite good for many electrons, fails for one electron. And it's not so much the fact that it fails in putting 50-50 of the electron left and right, but the problem is that it really likes this configuration, this 50-50, and all the others are not degenerate anymore, but they are much more expensive. And that affects in very radical way the potential energy surface for this system, in which Hartree-Fock, that is identical to Schrödinger, so it's exact, gives me this red curve. And LDA gives me this black curve that you see does quite a reasonable job in getting, say, the equilibrium geometry at 1 angstrom, the harmonic frequency, but gets completely wrong the dissociated state, because the dissociated state is the 50-50 state split in two. Now you understand that if red is the correct solution and black is the very wrong LDA solution, a standard hybrid functional like B3-lip is not going to do much better because it's going to, mix in a fraction of the correct one, Hartree-Fock, and most of the incorrect one. So, Hartree-Fock, B3-lip or all the short-range hybrids would also fail very miserably. And the failure comes from the atom. It fails because, as I said, density functional theory is very, very happy in its LDA-GG approximation to favor that 50-50 occupation whose energy is much lower than the 40-60, 30-70, 20-80, and so on and so forth. And in order to recover that degeneracy in energy here, what you would need is that the energy cost to extract, say, 10% of an electron from one side and put it back would be equal. So the energy cost to extract a fraction of an electron from a fractionally occupied atom should be matched exactly by the gain that you get when you put that fraction of an electron back in the other atom. That doesn't happen, so the energy of an atom is not linear with respect to fractional occupations, and it's actually favored. Here, the energy that should be linear, it's plotted in this paper by Wei-Tao Yang as the zero reference, so the energy should be linear, it becomes at zero reference energy, and what we have is that the 50% configuration is by far much more favored. So how do you put back this linearity in density functional theory? Has been a fun project of us for a long time. I'll go very briefly, so in 6-7 minutes we are going to be done. So one way where we started to put back this linearity was following the ideas of Matteo Coccoccioni and Stefano De Gironcoli that actually looked not at the hydrogen molecule, but were thinking maybe at a transition metal ion embedded in an oxide, where, maybe the transition metal ion can have an oxidation state, maybe it's an iron, it's a 2+ and a 3+. So it's the same problem. You need to decide, is the electron staying on the 2+ state? Is it going to be on the 3+ state? Is it going to be split? So in the solid state, we have this equivalent. And what they said is that as a function, and this is a heuristic statement now, because it's not anymore the clarity of one electron and the hydrogen molecule. It's maybe one electron in the solid that has to decide where to stay with respect to the iron 2+ and the 3+. But what they said is, well, exact DFT again should have an energy that is piecewise linear with respect to fractional occupations. If we do a calculation, I haven't used colors today, that's very sad, so I'll do it today. If we do a piecewise linear calculation, instead it looks a bit like this, it's quadratic, this is a better curve. And actually in reality this curve should not go up again, but this is how it was plotted. And what Matteo Coccoccioni said, well, if red is right and black is wrong, the difference between right and wrong is this blue curve down here. You see, this is what I need to add actually to the black curve to get the red curve that is correct. And what is the blue curve? The blue curve here is nothing else what the Hubbard U correction is. I'm writing it in a fancy way, but it's basically occupation times 1 minus occupation, where the occupation is the occupation of the Hubbard manifold. So it's a projection of that manifold of 3D electrons. And U is just the strength, so it's the height of this curve. So the Hubbard approach in density functional theory has really nothing to do with correlation. It's to do with the spurious curvature of the energy as a function of the fractional occupation of the Hubbard manifold. And this curvature is really a second derivative, so you can calculate it with density functional perturbation theory, and you can add it to the system and get now back the right result. You remove this curvature, this delocalization error with a u that is not a fitting parameter, but is calculated from first principle as the spurious curvature that we have around here. And if you do that, you recover very good results. I'll show you an example in a moment, but it's important, to say that, at least in my view, when we have this model corrections to LDA, GGA in DFT, even if it came from the Hubbard model, it has nothing to do with correlation anymore. It's just a self-interaction correction, occupation times 1 minus occupation as being the simplest quadratic correction to that lack of linearity. And you can see it very nicely, I think, in a system that we'll study in a moment, an iron olivine, where what I'm looking is the change in occupation on, say, one iron atom, what I call Fe3, when I change another occupation on another iron atom. So here I'm changing the occupation on one iron, and I'm looking at what happens. And what happens is that the other iron doesn't change occupation, it's flat, and what changes is the occupation of the ligands around iron 1. So this is to say that, you see, in this system there is no correlation. The iron atoms don't talk to each other, and what the U is doing is just controlling the amount of charge transfer between the transition metal ion and its ligands. And you can sort of, demonstrate that very clearly by looking actually at a system that has nothing to do with the Hubbard model. There is only one iron atom. So this is a chemical reaction of a methane molecule falling on an iron oxide dimer that we did many years ago with Edgar Kulik. And, if the Hubbard model was about correlation in density function theory calculation, this has nothing to do with correlation. But in reality, it has all to do with the spurious curvature and self-interaction. And so what we can do in this system, this is so small that we can do multi-reference configuration interaction in the right multiplet state, either in the sextet or in the quartet. And you see, if we do a density functional theory calculation with GGA in the sextet or the quartet, the errors are huge, are of the order of 2 electron volts. And we switch on the U, and it becomes much, much better. It has cured that huge amount of self-interaction that make the iron atom over hybridize with the oxygen. And actually, if I go back to the olivine, what happens is that, and this is more recent studies, is that while the U is great in general to correct most of the error, it tends to favor a little bit the atomic ionic solution, because the U is like this, so it wants to make the occupation of the Hubbard manifold 0 or 1, and that messes up systems in which there is also a certain amount of covalences. So the U kills a little bit too much the covalences, and adding in the Hubbard model also an intersite term between the transition metal and the ligand, and again calculating, we call it V, that second derivative with linear response theory, we seem to have a theory that starts to describe very well transition metal oxides, not only in this case the energetics, but also you see the configuration. Here we have a mixed valence configuration, 2+ and 3+, and you see LDA plus, LDA without a U makes the two ions have almost the same occupation. The U switches on some contrast between the two atoms, but that is very much sensitive to the U. And if you add also the intersite term, you get not only contrast, the 2+ and the 3+ are different, but they are the same that they were in the fully 2+ system, or the same that they were in the fully 3+ system. Okay, let me conclude with a last example, but I think go very, very fast. It's just that it's something I'm very happy with, so I wanted to show. And the idea was how we can generalize this to try and get actually spectral properties, not the energy from a functional. We cannot do it with a static potential, but we can do it with a dynamical potential. And so we can do it with a theory that depends on from a dynamical quantity, like the spectral density, or in a quasi-particle approximation from the orbital densities. And so what we have been working in the last few years, among other things, is building spectral theories that depends on the orbital density, using this concept of self-interaction as the driving force. That is the fact that the expectation value of the Hamiltonian should not depend on the occupation of the orbital. That is, if I take out of my interacting system a fraction of an electron, because that electron doesn't interact with itself, this expectation value should not change. How do we enforce this linearity? Well, this is what we do in this Koopman's functional, that is, we purify orbital by orbital like the U did, but in a more general way, not on just the Hubbard manifold. On every orbital, we purify the energy by removing the quadratic term and adding a term that is linear in the occupation, where the slope is calculated by taking the average of the slope, since that the endpoints are good in DFT, by the average of the slope, that is the integral between 0 and 1 of the energies. I won't go maybe into the details, I'll just show you a few results. Now, if you do this at frozen orbitals, you're not taking into account screening, so you need to put back some screening coefficients. When you do that, you get a functional that is still a functional of the density, but is also a functional of the orbital density. So it's beyond the density functional theory, and it's really more like a quasi-particle approximation to a spectral theory. But once you do that, I think the results are remarkable. This is a standard set of 100 molecules. So this is more impressed now. It's been published. 100 molecules, and these are the errors, the mean average error or the mean signed error, the absolute error, in the ionization potentials of 100 molecules. And you see here a variety of techniques, including, all the different flavors of GW, and this Koopman's functional actually do a great job, very, very inexpensively. These are photoemission spectra, again, very good agreement in the peaks. And for reasons that I don't have time to discuss, they also work equally well in the solid state limit. And we get band gaps now that are right, I think, for the right reasons, with errors of 0.2 electron volts that are much, much better than GW and are comparable to the state of the art of self-consistent GW with vertex correction, but having also the position of the valence bands actually quite a bit accurate than that state of the art. Okay, let me conclude. I hope that you have been staying around. Let me see how many people we have. Well, 175. That's great. This was just a conclusion on this Koopman's functionals. I won't go into detail. Many other groups are thinking, but I know why you have been hanging around, because you actually wanted to know at the end of the story why is DFT like Tinder. And so this is the answer to this riddle. I'm very proud to give it to you. So first of all, DFT, as you have seen, is very popular. More than 30,000 papers published every year. And it's fast and it's quite easy. And, these days you can think very little, just use, the quantum espresso input generator, the quantum mobile, and you get a result. Hopefully it'll be correct. I've tried to teach you how to get it correct, and especially to point you to a lot of study material where you can learn. But the most important thing is that you can swipe functional left until you find one that works for you for a while. So with this, here is more thoughts on this if you're interested. Let me conclude. There are a lot of people that I want to thank. I didn't have time today, it was very rushed to put their picture, but these are the people I learned from you know, my undergraduate years, my first papers with Mauro Ferrari, learning electronic structure from Alfonso Baldereschi, doing my first research project with Stefano Baroni. You know, lifelong friendship with Alessandro De Vita is not here with us anymore, but is the person that really helped me make all my most important professional decision in life. So I really owe him a lot. Mike Payne was my PhD supervisor. David Vanderbilt was my postdoc supervisor, and Roberto Carr. After that, before starting a scientific life of my own with many, many people, I forgot to thank the panelists today, Loris Ercole, Davide Campi, Michel Kotiug, and Yuri Timrov, that have been capturing your questions. But the list of people in the group from the very first students at MIT 20 years ago, and the very first postdoc, and everyone is listed here. Now we have some more conclusions that are more general. They'll just take 30 seconds. I haven't written them down. Maybe it's actually better that I haven't written them down. I hope to have given you a sense of how powerful computational science can be, and especially how powerful it is when it is based on quantum mechanical methods, especially methods that can be accurate and precise like density functional theory, or other methods that can be accurate or precise for the right reasons, maybe more expensive, but we can do that. I also think that very few people have understood the power of computational science and what it can do for scientific society, for technological development. I think the way science is funded is still thinking at you know, the Manhattan Project, the big infrastructure projects, and politicians need you know, a big building to be photographed in front of. And no one thinks actually what is the development model that is needed for computational science. Maybe we are lucky the Swiss National Science Foundation with Marvel has given us funding for 12 years. We're in the middle of it with Marvel to try and find a way. And it's even ever so more remarkable because computational science can be truly open science. If we develop something, everyone in the world can benefit from it at the same time, while traditional science made with brick and mortar infrastructure can only be accessed to those that have access to that brick and mortar infrastructure. Either they are lucky, or they are wealthy, or they are good and they have won access to it, but it's limited in its scaling, while computational science can be disseminated everywhere, and every development can be disseminated everywhere. We just don't have the right economical and scientific model to develop it. I've been bewildered for 20 years by how much this is not happening almost anywhere. And I hope that in the rest of my scientific career, I'll manage to convince you and policymakers that there is a lot to be gained to change that model. It really costs very little, but we just don't have the right tools. With this, as they say, it's been a pleasure and an honor to do this, to have your attention for so much time. This will be on the web, so others might benefit for it. You know how to get in touch. There is a mailing list you can subscribe to. And so I would close saying, be well, do good work, and keep in touch.